February 20th, 1943, north of Kasserine Pass, Tunisia. A German after-action report would later try, and largely fail, to describe what tank commanders of the 10th Panzer Division watched that morning. 5 American Sherman tanks, separated by broken terrain with no direct line of sight between them, converged on German positions with a timing that read, to the men watching it happen, as something close to supernatural. No flags, no flares, no dispatch riders sprinting between vehicles under fire to relay orders by hand. The method German doctrine still assumed would be necessary the moment radio contact failed. The 5 tanks moved as a single coordinated formation, each covering ground the others could not see, each crew apparently certain where every other crew in the formation actually was. In the German Panzer IVs opposing them, tank commanders equipped with FUG-5 radios were straining to hear their own platoon leader through static that their amplitude modulation receivers had no way to filter out. The German transmitter, 10 watts of output, struggled to carry a clear signal more than a few hundred meters once the tank itself was moving. Engine vibration, track noise, and the tank's own electrical system all bleeding directly into the same frequency band the operator was trying to receive on. Most tanks in a standard German platoon carried a receiver only, with no transmitter at all. They could hear an order from the platoon leader's vehicle, but had no way to report what they were seeing or request help of their own. The specific German officer who filed the intelligence assessment on this engagement, his name lost to the surviving fragment of the document, though the unit designation is clear, used a phrase that later translators rendered roughly as coordinated as if by telepathy, a description that, whatever its intended rhetorical weight, correctly identifies the actual mechanism while completely failing to name it. There was no telepathy. There was a piece of American electronics weighing 181 pounds, bolted into the hull of every Sherman on that battlefield, that the German officer had no framework yet to recognize for what it was. The Americans were operating equipment the German army did not know existed in the form it actually took. Frequency modulation radios, standard in every single tank rather than reserved for command vehicles. Crystal controlled for frequency stability. Transmitting at 25 watts with a clarity that cut through engine noise and battlefield chaos in a way German engineers, working from an entirely different technical foundation, had no ready means of matching. Some 8,000 kilometers from the Detroit area factory floor where the relevant components had actually been designed and produced, one of the decisive technological asymmetries of the European war was making its first serious battlefield appearance. Not in armor thickness, not in gun caliber, but in a part of the electromagnetic spectrum neither side's infantry could see. The specific American decision that produced this gap dated to July 22, 1941, when the U.S. Army Signal Corps standardized the SCR-508, SCR-528, and SCR-538 radio sets as required equipment for every medium tank in the inventory. A decision made 5 months before Pearl Harbor, while German armored formations were still advancing successfully through the Soviet Union, using tactics that depended on exactly the kind of radio coordination German industry would, within 2 years, prove structurally unable to sustain at scale. The engineering behind the American sets came from an unlikely source, the Galvin Manufacturing Corporation of Chicago, a company that before the war built car radios and would become known after it as Motorola. Daniel E. Milble, who had done early academic work on frequency modulation theory, conceived the specific application of FM technology to a combat vehicle's electrical environment. Henryk Magnuski, the company's principal RF engineer, solved the harder practical problem of making sophisticated crystal-controlled electronics survive the vibration, temperature extremes, and electrical interference that a tank's own engine and drivetrain generated as a matter of course. Magnuski's own background is itself a small illustration of the kind of talent American wartime industrial mobilization was able to draw on. A Polish engineer who had emigrated before the war, he brought a European technical education to bear on a specifically American manufacturing problem, and his solutions to the shielding and grounding challenges that a tank's chassis presented to sensitive radio electronics became, in modified form, standard practice across the rest of the American tank radio program. Installing the set at the factory, rather than as a battlefield retrofit, meant every Sherman rolling off the assembly line arrived radio-equipped from the outset, which in turn allowed the Army to build radio operator training directly into standard tank crew instruction, rather than treating it as specialist follow-on schooling reserved for a designated signals soldier. A driver or loader could, if needed, step into the radio operator's seat and function adequately, because the equipment and its basic operation had been part of every crew member's baseline training, rather than the exclusive competence of one man. In practical effect, this turned every Sherman into a node in what later military historians would describe as history's first genuine battlefield communications network. The BC-604 transmitter at the set's core generated 25 watts of output, 2.5 times the German FUG-5's rated power, operating across a 20.0 to 27.9 MHz band with 10 preset crystal-controlled channels a crew could switch between instantly, rather than manually retuning a variable capacitor under fire. The SCR 508 configuration paired this transmitter with dual BC-603 receivers, letting a tank commander monitor his own platoon's frequency and his company commander's frequency simultaneously, a capability that mattered enormously in practice because it meant orders could flow downward and situational awareness could flow upward through the same physical set without either channel blocking the other. The technology's real advantage, though, sat one level beneath the specific hardware. Edwin Armstrong's frequency modulation principle itself, licensed by its inventor to the U.S. military, which eliminated most of the static and electrical interference that plagued amplitude modulation systems, by design rather than through any amount of careful shielding. Armstrong himself had spent much of the 1930s fighting a bitter, largely unsuccessful commercial battle to get FM radio adopted for civilian broadcast against the entrenched interests of AM radio manufacturers and networks, a fight he was, by most accounts, losing in the civilian marketplace, at the exact moment the U.S. military recognized the same technology's specific value for a problem the civilian broadcast industry had never needed to solve: keeping a signal intelligible inside a moving, vibrating, electrically noisy steel box. Where a German FUG-5 receiver picked up every spark plug discharge and every nearby electrical motor as audible noise layered directly over the intended signal, an American FM receiver rejected most of that same interference as a structural property of how frequency modulation encodes information. Clear voice communication was achievable even during an active artillery barrage, a condition under which German AM sets frequently became unusable, regardless of how skilled the operator was. November 8, 1942. Operation Torch brought American armor to North Africa for its first sustained combat test, and the 2nd Armored Division's tanks came ashore near Safi and Fadala, already fitted with SCR 508 sets, whose practical superiority over German equipment had, at that point, never been demonstrated in actual combat conditions. The Afrika Korps, for all its reputation as the Wehrmacht's most experienced and professionally regarded armored formation, operated under communication constraints that its own doctrine had never fully solved. A standard German tank platoon of 5 vehicles typically included only 1 or 2 tanks fitted with a full FUG-5 transceiver, capable of both transmitting and receiving. The remaining 3 or 4 carried FUG-2 receivers only, meaning those crews could hear the platoon leader's orders but had no mechanical means of reporting an enemy position they had just spotted, or warning the rest of the platoon about a threat offering from an angle the leader's own vehicle could not see. German tank platoons functioned, by structural necessity rather than doctrinal preference, through a rigid hierarchy in which subordinate crews acknowledged orders through action rather than voice reply. And the platoon leader's vehicle, identifiable at a distance by its distinctive multiple antenna configuration, was consequently the single most valuable individual target on the battlefield. Destroy it, and the remaining 4 tanks lost coordinated direction almost immediately, since none of them possessed the equipment to reorganize a chain of command among themselves. Kasserine Pass, fought February 14th through 24th, 1943, remains remembered primarily as a German tactical victory, and that assessment is accurate as far as it goes. But the battle also produced the first substantial documented evidence of the specific communications gap that would define the rest of the war in this domain. Amid the genuine confusion of the fighting, scattered elements of the U.S. 1st Armored Division maintained coordinated contact across roughly 50 miles of battlefield. Tank crews who had never previously operated together, warning one another of approaching threats and calling in artillery support through FM channels clear enough to be intelligible under conditions that would have reduced a German AM set to unusable static. German signals intelligence, intercepting these transmissions as a matter of routine practice, filed reports specifically noting the unusual clarity and coordination. The 10th Panzer Division's own intelligence section observed that American units were maintaining reliable contact at ranges where equivalent German transmissions produced nothing but noise, and, more unsettling to the officers reading the report, that every individual American tank appeared capable of full two-way transmission, rather than the small minority of specially equipped command vehicles German organizational doctrine assumed was structurally necessary. The tactical irony of Kasserine specifically is worth pausing on. The battle is remembered, correctly, as an American defeat, and the same intelligence reports documenting superior American radio coordination were filed by the winning side. This is not a contradiction. Radio superiority alone did not compensate for the American formation's inexperience, the poor initial dispositions of forward units, or Rommel's own considerable tactical skill in exploiting the terrain and the gaps in the American line. What the radio advantage did was prevent the defeat from becoming the total operational collapse it might otherwise have been. Scattered American units, cut off from their original chain of command by the speed of the German breakthrough, were nonetheless able to re-establish coordinated resistance with whatever nearby friendly units they could reach by radio, rather than each fighting or fleeing as an isolated element with no ability to reconstitute a coherent defensive line. This distinction between losing a battle and losing an army is precisely the distinction German intelligence officers were groping toward when they described American coordination as unsettling even in the context of an engagement their own side had clearly won. The German FUG-5's specific technical limitations, measured against this performance, extended beyond raw transmission power into the physical geometry of the antenna itself. The set's whip antenna, mounted rigidly to the turret roof, was tuned to a fixed length that assumed a stationary or slow-moving vehicle. German signals manuals from the period specify a precise antenna angle for optimal reception that a tank commander had no practical way to maintain once his vehicle began crossing broken ground at speed, meaning the set's already limited range degraded further from mechanical mistuning on top of the interference problem alone. September 1943 brought American armor to Italy, into mountainous terrain that should, on paper, have neutralized any radio advantage entirely. Steep valleys, ridge lines blocking direct line of sight, the kind of multipath signal reflection that degrades most radio technology regardless of its underlying modulation scheme. Instead, FM technology proves specifically better suited to exactly these conditions than the alternative. Because frequency modulation's resistance to the kind of signal distortion mountain terrain produces gave it a structural advantage AM technology could not replicate through any amount of additional power or antenna placement. The physics behind this specific advantage is worth stating plainly, because it is easy to assume all radio technology suffers equally from difficult terrain. Amplitude modulation encodes information by varying signal strength, which means any interference that alters signal strength, including the kind of reflected delayed echo a signal produces bouncing between steep valley walls, directly corrupts the transmitted information. Frequency modulation encodes information by varying signal frequency instead, a property that reflected, delayed copies of the same signal disturb far less severely, since the receiver can generally still extract the correct frequency pattern even when multiple slightly time-shifted versions of the same transmission arrive simultaneously. This was not a design feature American engineers specifically built for mountain warfare. It was an incidental consequence of the underlying modulation choice that happened to matter enormously once the fighting moved from North African desert to the Apennines. American armored units advancing toward Cassino coordinated movement across terrain where visual signaling was categorically impossible, and where German radios, by multiple independent after-action accounts, failed outright rather than merely degrading. Tank platoons separated by entire ridge lines executing coordinated attacks German doctrine held required direct visual contact between vehicles to accomplish it all. June 6, 1944. Sherman tanks coming ashore at Normandy maintained radio contact with naval fire support offshore throughout the landing, a level of ship-to-shore coordination German technology of the period had no equivalent means of achieving. But the bocage fighting that followed exposed a genuine structural gap in the American system rather than confirming its universal superiority. Tank radios operating in the 20.0 to 27.9 MHz band could not communicate directly with infantry radios, which used the separate SCR 300 backpack set operating at 40.0 to 48.0 MHz. The incompatibility proved lethal in specific, documented instances through the hedgerow country, where German infantry armed with Panzerfaust anti-tank weapons could approach an American Sherman at close range, while nearby American infantrymen, unable to warn the tank crew over an incompatible frequency, had no reliable way to alert them before the German infantryman was within effective range. American units solved the problem within weeks through a field improvisation rather than a formally issued equipment upgrade. Crews mounted standard EE-8 field telephone handsets in ammunition boxes welded onto the rear exterior of the tank hull, wired directly into the vehicle's internal intercom system so that an infantryman walking beside the tank could pick up the handset and speak directly to the crew inside without either side needing compatible radio frequencies at all. By the opening of Operation Cobra in late July, the modification had spread widely enough across First Army's armored units to function as an unofficial standard. A specific example of tactical adaptation generated at the unit level and propagated informally rather than mandated top-down, in a period measured in weeks rather than the months of formal equipment change through official channels would ordinarily have required. July 25th through 30th, 1944. Operation Cobra demonstrated what fully integrated American radio coordination looked like at the scale of an entire armored division rather than a handful of tanks. The 2nd Armored Division, under Major General Edward H. Brooks, coordinated more than 200 Shermans through radio networks that gave German defenders of the Panzerlehr Division the specific, disorienting impression of facing an enemy that somehow already knew where every threat was before it fully materialized. American tanks responded to reported threats identified by other units miles away with a speed that had no equivalent on the German side of the line. Artillery strikes, coordinated directly through tank radios, landed within minutes of a target being identified, rather than the much longer cycle a request routed through conventional forward observer channels required. Panzerlehr, once regarded as one of Germany's premier armored configurations, had by this point in the campaign been reduced to what amounted to communications poverty. Most of its remaining tanks operated without functioning radios of any kind, depending on visual signals in terrain where sight lines rarely exceeded 100 meters. The handful of sets that still worked suffered from the same interference and range limitations that had already been well documented at Kasserine 18 months earlier, with no meaningful technical improvement having occurred to German equipment in the interval. The irony embedded in this specific gap deserves stating plainly, because it complicates any simple narrative of German technical backwardness. Germany had, in fact, pioneered the serious integration of radio into armored doctrine in the first place. Heinz Guderian, the principal architect of Blitzkrieg doctrine, had insisted on radio equipment as a core requirement for tank operations since the 1920s, and his 1937 book, Achtung Panzer, treated reliable communication as functionally inseparable from the entire concept of rapid, coordinated armored advance. Guderian understood, earlier and more completely than most of his contemporaries in any army, that a fast-moving armored formation was only as effective as its ability to coordinate in real time. In this specific sense, German doctrine had correctly identified the exact problem American engineers would go on to solve more completely nearly 2 decades later. The conceptual insight was not the failure. What German industry could not do, by 1943, was actually manufacture radio equipment at anything close to the volume Guderian's own doctrine required. German production that year yielded approximately 5,700 medium tanks against fewer than 2,000 FUG transceivers, a shortfall that forced allocation decisions concentrating the available sets in command vehicles and assault guns, leaving the great majority of ordinary line tank crews with receive-only equipment, or, in a substantial number of documented cases, no radio at all. Guderian himself, serving from 1943 onward as Inspector General of Armored Troops with direct visibility into exactly this production shortfall, raised the problem repeatedly through official channels. A December 1944 memorandum under his name acknowledges explicitly that American coordination capability was negating German advantages in individual tank quality, a remarkably candid admission from an officer whose entire pre-war career had been built on the premise that Germany's approach to armored warfare was conceptually superior to anything its opponents had developed. Guderian's own authority within the wartime German military apparatus was by this point insufficient to redirect the raw material and skilled labor allocation that would have been required to close the gap, regardless of how clearly he understood the problem, or how forcefully he raised it. Soviet forces, for comparison, fared considerably worse on this specific dimension, despite fielding the most numerous Allied tank of the war. The T-34, in its most widely produced early variants, typically entered combat without any radio equipment whatsoever. Soviet armored doctrine through 1941 and into 1942 relied on flag signals and pre-battle planning fixed before contact, with consequences against German formations that Soviet after-action reports from the period describe in terms considerably harsher than anything German assessments of American capability ever employed. Lend-Lease shipments beginning in 1943 provided some relief, equipping Soviet command tanks with American SCR-508 sets, among other imported equipment. But even by the war's end, only an estimated 25% of Soviet tanks carried any radio at all, against the 100% deployment rate the American Sherman fleet achieved across its entire production run. The comparison across all three major Allied and Axis tank-producing powers is instructive, precisely because it rules out the simplest possible explanation for the American achievement. This was not merely a case of one wealthy nation outproducing poorer rivals in some general sense, since the Soviet Union, despite enormous American material assistance specifically targeted at closing this gap, never approached German or American deployment rates for tank radios, even with millions of dollars of imported equipment arriving through Lend-Lease. The specific combination of industrial capacity and pre-war institutional decision-making that produced universal American deployment was not, it turns out, straightforwardly transferable, even with substantial external material support. The manufacturing effort behind that 100% figure represented American wartime industrial mobilization operating close to its practical ceiling. Motorola's Chicago plant, converted from pre-war car radio production, had to solve manufacturing problems with no close pre-war precedent. Each SCR-508 set required 2,748 individually manufactured components, assembled to tolerances the company's existing car radio production lines had never needed to meet, and the BC-604 transmitter alone contained 474 capacitors and 385 resistors, each of which had to hold its specified value despite the temperature extremes and sustained mechanical vibration a combat vehicle's interior actually produced. Crystal oscillators, the specific component responsible for the set's frequency stability, had to maintain their calibration within a fraction of a percent across conditions that would have detuned a less carefully engineered design within hours of continuous operation. Production climbed steeply once the manufacturing problems were solved. Roughly 3,800 units of the SCR-508 family in 1942, 11,400 in 1943, and 24,000 in 1944, for total wartime production exceeding 50,000 tank radio sets across the full run, a volume sufficient to equip all 49,324 Sherman tanks manufactured during the war with sophisticated FM radio equipment as standard issue, an achievement no other combatant nation approached at comparable scale. The SCR-508's specific technical advantages extended well past its headline power and modulation figures. Crystal-controlled frequency stability meant a crew could preset 10 channels before an engagement began and rely on those channels remaining correctly tuned throughout sustained combat, where the German FUG-5's variable capacitor tuning mechanism was prone to drifting off frequency under exactly the vibration and temperature stress combat imposed. The dual receiver configuration let a commander monitor his platoon's internal net and his company's command net simultaneously, rather than choosing between them. An integrated BC-606 intercom system let every crew member alert the tank commander to a threat instantly through a throat microphone and noise-canceling headset, equipment many German tank crews lacked entirely, forcing communication inside the vehicle itself to depend on touch signals or shouting over engine noise, a limitation that slowed internal crew coordination even before any external radio problem entered the picture. Power management provided a further quiet advantage. The SCR-508 operated on either 12 or 24 volts, adjusting automatically to whatever the vehicle's electrical system supplied, drawing power through a dynamo motor supply that filtered out much of the electrical noise a direct connection to the tank's own ignition and starter systems would otherwise have introduced. Precisely the kind of interference German radios, wired more directly into the vehicle's electrical system, picked up as a matter of routine. The tactical consequence of universal, reliable radio deployment reshaped American armored doctrine at a structural level, rather than simply making existing tactics execute faster. The Combat Command System. Flexible task forces assembled on short notice from whatever combination of tank, infantry, artillery, and engineer units a specific mission required, rather than fixed, permanent formations, depended entirely on the assumption that any two American units, regardless of their parent organization, could establish reliable radio contact and coordinate effectively on short notice. This flexibility, which German officers found genuinely difficult to parse when they encountered it, was possible specifically because compatible, universally deployed radio equipment removed the coordination risk that would otherwise have made ad hoc unit combinations dangerously unreliable in combat. At Ericourt in September 1944, the 4th Armored Division faced multiple German panzer brigades equipped with individually superior Panther tanks, heavier armor, a more powerful main gun, genuine technical advantages in a direct one-on-one engagement. The German formations committed to the battle were, on paper, a formidable force. Several newly formed panzer brigades rushed to the front specifically to blunt Patton's advance through Lorraine, crewed in part by veterans transferred from the Eastern Front and equipped with some of the most capable individual armored vehicles Germany still had in serious production. American radio coordination proved decisive against those technical advantages regardless, and the specific tactical mechanism deserves description in some detail because it illustrates the broader principle at battlefield scale rather than merely in the aggregate statistics. Persistent morning fog across much of the engagement reduced visibility to a few hundred yards in places, conditions that should, by conventional tactical logic, have favored the side with individually more powerful guns and thicker armor able to survive a close-range surprise encounter. Instead, American tank destroyer crews and Sherman gunners, unable to see more than a short distance in any single direction, could nonetheless receive real-time reports from other American units elsewhere on the field that could see clearly, effectively extending each crew's situational awareness far beyond what their own eyes alone could provide through the fog. Every Sherman in contact could report an enemy position instantly to units that could not themselves see the target. Tank destroyers received targeting data from tanks positioned elsewhere on the battlefield, and artillery observers riding in specially equipped command tanks called devastating concentrated fire within minutes of a target's first identification. German formations, by contrast, found the same fog considerably more costly. Without equivalent inter-unit reporting, individual German tank crews were functionally as blind as their American counterparts, but lacked any mechanism to compensate for that blindness with information gathered elsewhere on the battlefield. Over 3 weeks of fighting, the 4th Armored destroyed 281 German armored vehicles while losing 41 Shermans of its own, a roughly 7-to-1 kill ratio achieved against an opponent that held a clear individual vehicle technical advantage in every direct engagement, a result the raw armor and gun specifications on each side would not have predicted. Post-war analysis of the engagement, conducted separately by both American and German military historians, studying the battle specifically as a case study in armored doctrine, converged on broadly the same conclusion. The outcome at Ericourt cannot be adequately explained by any factor other than the American formation's ability to fight as a single coordinated system under exactly the low visibility conditions that should have neutralized that advantage, rather than negated it. German intelligence, across the full span of the campaign, consistently failed to correctly diagnose the source of American coordination advantage, even while documenting its symptoms repeatedly and in considerable detail. A captured German assessment from September 1944 recorded that American tank units demonstrated good radio discipline and coordination, attributing the observed pattern to extensive training and rigid communication procedures, a conclusion that entirely missed the underlying technological gap, treating what was substantially a hardware and industrial capacity problem as though it were purely a matter of training doctrine. German formations could, in principle, match through better discipline alone. German tactics never meaningfully adapted to the actual capability gap. German gunners continued prioritizing tanks identifiable by prominent multiple antenna arrays as command vehicles worth targeting first, without recognizing that in an American formation, nearly every tank carried equivalent transmission capability, and destroying one particular vehicle produced none of the coordination collapse that destroying an equivalent German command tank reliably did. March 1945. As American forces approached the Rhine, the accumulated communications advantage reached what amounted to its practical peak. When the 9th Armored Division discovered the Ludendorff Bridge at Remagen still intact, radio reports reached 1st Army headquarters within minutes of the discovery. Within roughly an hour, formations across the entire front were already receiving orders to redirect and exploit the unexpected opportunity. German forces, dependent through much of this period on telephone lines that Allied air power had been systematically targeting for destruction, had no comparable capacity to respond at matching speed. A German counterattack against the bridgehead, coordinated poorly by units that had lost most of their wire communication and had no adequate radio alternative, arrived in fragments rather than as a single coordinated assault and was defeated in detail as a direct consequence. April 1945. The encirclement of the Ruhr pocket represented the culmination of this specific advantage at the scale of an entire army group. American armored columns from 1st and 9th Armies coordinated a complex double envelopment almost entirely through radio communication across a front spanning hundreds of miles, closing the pocket around roughly 325,000 German troops of Field Marshal Walter Model's Army Group B, trapped in substantial part because their own internal communications had already collapsed before the physical encirclement fully closed. American fighter bombers, guided by radio-equipped forward air controllers working in direct coordination with the advancing ground formations, specifically targeted the communications nodes that remained functional inside the pocket, accelerating a collapse already underway. Model's own final surviving messages, before his headquarters lost coordinated contact with its subordinate formations entirely, describe the specific character of the breakdown directly. No contact with adjacent units, no communication with higher headquarters. Fighting continuing, but effective coordination no longer possible. The scale of the Ruhr encirclement makes it a useful closing data point, precisely because it removes any remaining ambiguity about whether the earlier engagements at Kasserine and Ericourt represented isolated tactical successes rather than a repeatable structural advantage. An operation coordinating 2 full field armies across a front measured in hundreds of miles, closing simultaneously on a target the size of an entire German army group, is not the kind of result a temporary tactical edge, or a single skilled commander's improvisation, can plausibly explain on its own. It requires, at minimum, a communications architecture reliable enough that Army-level staff could trust radio reports arriving from formations they could not otherwise verify in real time. The same underlying property, scaled up by roughly 3 orders of magnitude, that had first become visible in the 5 Sherman tanks converging on a German position outside Kasserine 2 years earlier. The psychological dimension of this asymmetry deserves separate attention from its purely tactical consequences, because it shaped the individual combat experience of tank crews on both sides in ways the statistics alone do not fully convey. American crews fought with the specific, continuous knowledge that they were never genuinely isolated. Even a tank physically separated from the rest of its formation by terrain or smoke remained connected through a radio link that functioned regardless of what could or could not be seen. German tank crews, particularly by the war's later years as functioning equipment grew scarcer, experienced something closer to the opposite. Individual isolation within a larger engagement whose overall shape they frequently could not perceive. Fighting a series of separate individual battles rather than a single coordinated action even when nominally part of a larger formation. Field Marshal Wilhelm Keitel's reported remark at Germany's surrender, that Germany had known how to build better tanks, but the Americans had known how to make them work together, captures a real distinction, whether or not the specific quotation survives close scrutiny as verbatim. The radio gap produced a specific, measurable secondary effect on crew survivability that rarely appears in the standard armor versus gun comparison. A Sherman crew that spotted a threat and radioed a warning before making contact gave every other crew in range a chance to reposition or return fire first, while a Panther crew operating without a working link to its neighbors typically discovered a flanking threat only when it was already close enough to engage directly. Post-war Army studies of Sherman loss patterns found a disproportionate share of German kills against American tanks occurred in the first minute of an engagement neither side had anticipated. Precisely the window a functioning radio network was built to close, and precisely the window an isolated German crew, however well armored, had no equivalent tool to manage. After Germany's surrender, American technical intelligence teams conducting a systematic evaluation of captured German armor confirmed in detail what combat experience across multiple theaters had already suggested. U.S. Army Technical Intelligence Report number 176 concluded that German tank communications equipment lagged American systems by approximately 5 years in underlying technical sophistication, The absence of frequency modulation, the limited distribution of full transceivers across ordinary line units rather than command vehicles alone, and inadequate electrical interference suppression, combining into a set of vulnerabilities the report characterized as structural rather than merely a matter of wartime production shortfall. Soviet post-war technical evaluators, working from their own access to captured German equipment, reached broadly similar conclusions, and specifically chose to base post-war Soviet tank radio development on American rather than German designs. A decision made by military engineers with direct comparative access to both systems, and one that speaks more plainly to which approach they judged superior than any wartime propaganda from either side could. The principle this specific technological gap established has persisted well beyond the conflict that first demonstrated it at scale. Modern main battle tanks carry integrated communication suites that trace a direct conceptual lineage back to the SCR 508, digital rather than analog in their underlying technology, but built on the same foundational premise of universal deployment and reliable real-time coordination across an entire formation, rather than communication reserved for a small minority of designated command vehicles. West Germany's post-war Bundeswehr, rebuilt in the 1950s with the lessons of its predecessor's specific communications failure directly in mind, prioritized radio equipment from its earliest doctrine documents forward. Every Leopard tank subsequently manufactured has carried comprehensive communication systems as standard rather than optional equipment. And Bundeswehr training material has, at various points, explicitly cited the specific historical case of individually inferior American tanks defeating individually superior German ones through superior coordination as a formative lesson in what the doctrine calls information dominance over platform superiority. The same underlying principle has recurred in conflicts considerably removed from the Second World War's specific technology and terrain. In the 1991 Gulf War, coalition forces built around superior networked communication defeated Iraqi armored formations equipped with individually respectable Soviet-derived tank designs that lacked comparable coordination capability. The pattern repeated again in 2003. In each case, the specific hardware separating the two sides changed completely. The underlying structural principle, the SCR 508, first demonstrated at scale in the deserts of Tunisia, did not. Here is the forensic summary. The production choice underlying this outcome traces back to a specific institutional habit rather than a single dramatic decision. American ordnance planning in the interwar years had treated communications equipment as a line item requiring the same guaranteed production allocation as ammunition or fuel, evaluated separately from and never competing directly against the far more visible armor and gun specifications that dominated public and even much internal military discussion of tank design. German procurement, by contrast, treated radio sets as an accessory, fitted after the core vehicle was designed and funded, competing for the same finite pool of skilled electronics labor and raw materials that Germany's broader wartime economy was already rationing with increasing severity by 1943, a procurement hierarchy that made the FUG-5 shortfall not an isolated production failure, but the predictable output of where radios sat in the list of things German industry was told mattered most. Consider what a fix would actually have required on the German side, given everything documented above. Not a smarter tactic, German officers were, by the record, tactically resourceful under conditions far worse than communication trouble alone. Not better training, since the intercepted transmissions German signals officers were already reading demonstrated a level of coordination no amount of drilling could produce without the underlying hardware to support it. It would have required several thousand additional skilled electronics technicians, a reliable supply of crystal oscillators precise enough to hold frequency under combat vibration, and a decision made years before the shortage became visible on any battlefield to Poebel's radio production as a first-order priority, competing on equal footing with tank hulls and gun barrels, rather than as an afterthought fitted to whatever chassis survived the rest of the allocation process. None of that was available to correct once the gap had already opened in North Africa in 1943. By the time Guderian's own memorandum described the problem in writing, the industrial capacity to close it no longer existed anywhere in the German war economy, regardless of how clearly anyone in Berlin now understood what was missing. Guderian died in 1954, a year before West Germany's rearmament began in earnest. having spent his final years writing memoirs and consulting informally with Western military planners increasingly interested in his pre-war theoretical work on mobile warfare. His own memoir, Panzerleader, published in 1951, devotes extensive attention to the armor and strategic decisions that shaped the war's major campaigns, and, by most close readings of the text, only a few scattered lines to the specific communication shortfall his December 1944 memorandum had described in such plain terms. A curious omission from the one German officer whose earliest career had been built specifically on the argument that reliable coordination mattered more than any single piece of armored hardware.